Okay, let's start. Welcome to Big Data Driven, no, to Cloud Data Driven Online User Group Meeting. Our topic for today is index selection in SQL Server. The rule is you guys are free to comment, but do it with respect. There must be no offensive comments. Turn off the video and microphones. Our speaker for today is Grant, right? He's a Microsoft platform MVP and AWS community builder. He has over 30 years of experience in IT. He will introduce himself and give you more about his IT live experience. Our next presentation will be on February 18. The topic is using the Azure Data Platform to predict employee turnover. We will have Daniel Dean as speaker, and then we have a couple more Azure Logic app for Azure Database DBA. And also we have the Cloud Awaken Azure SQL Server for the on-premises DBA. I would highly suggest you guys to go and save your spot for that. And also there's a tons other session over there. If you guys want to present any session, feel free to email me at jjoseph@bigdatadriven.org. Now, Grant, I'm about to give to let you start with this session. Feel free to share your screen.
Okay. Oh, there it is. I lost where it was.
Yes,
There we go.
that happens sometimes.
I got it.
By the way, thank you so much, Grant. It is an honor to have you at Cloud Data Driven User Group.
Oh no, it's my pleasure. I'm happy to help out and take part. Any place I can get together and just blather at people, I'm willing to do it. So thanks for the opportunity.
You are
All
very
right.
welcome.
Well, let's go ahead and get started. For those who don't know, my name is Grant Fritchey. I do work for Redgate Software as the DevOps advocate. This is my contact information. I don't really put up about me slides because nobody cares. Nobody wants to hear, all kinds of stuff about people. What you want to know is where do you go for questions? And so here's my blog, my Twitter handle, and my email address. If you've got questions after today, I will try to help out. So please feel free to reach out and ask any questions that you have, and I will do my best to answer them. And that's pretty much all I'm going to say. Let's get started. This is a huge topic, an enormous topic. And fair warning, this is my second time doing this presentation. The first time took over 2 hours and I didn't finish everything. So I'm going to try to trim it down and limit what I talk about so that we can get through it. Now, I want to say this up front so you have a chance to run. There is no magic formula. There is no if A, then 1, if B, then 2 methodology that's going to let you index your SQL Server instances. Instead, it's understanding what those indexes are, understanding how those indexes work, understanding the role statistics play with those indexes, and then you can start to make choices. But even those choices are largely going to be guesses to a large degree because there is no single magic formula. And anyone who tells you they have a magic formula for picking indexes merely wants to sell you something. So be very cautious about that. I don't have a magic formula. So if you want to run now, now's a great time. You do not have to sit here when you're not going to get that magic formula that you're looking for. So if that's what you're after, I'm so sorry, but let's get going for everyone else. Indexes are really simple to understand. It's a sequential arrangement of material in alphabetical or numerical order. Done. Right? It's ordering information. That's all it is. Now, in the old days, we would talk about phone books. This is a card catalog, but you get the idea. Ordering data in a particular way. That's what indexing is. It's very simple. Now, when we talk about SQL Server, there's a limited number of index types. Now, you can go online and there's debates over, how do you define the type of index? Is a unique index a type of index, or is that a property of an index? I lean towards it's a property of an index. I'm not going to fight anyone who says it's actually a type of index. That's great. If you believe that, that's cool, good, go. But in general, there are a limited number of types of indexes. There's the row store indexes, either a clustered index or a non-clustered index. There's the column store index, and they are roughly the same. There's a clustered column store and a non-clustered column store. And then we get the specialty indexes, the XML index. How about now? Looks like it's off. Are you back? Are we back? I still can't hear you.
I'm not
There you are.
sure. Yeah, I'm not sure what happened, but what I did, I just have to, remove all access from everyone. It seems like somebody put you on mute. Yeah. So carry on. Thank you so much. Sorry about that, guys. Thank
I
you.
saw Jeff Moden come in. It was probably him. Totally teasing, Jeff. All right, so we'll keep going. So the XML spatial full text indexes, those are indexes specific to a data type. We're still sharing the desktop, right? Let's make sure. Yes, I am. Cool.
Yes, I can see.
Okay, cool. And then there's the hash index, which is an in-memory index for in-memory databases. It's a very different type of index. Now, here's the deal. Because this is such a huge topic, because there's so much to cover, and because I'm not even going to be able to cover everything I need to cover on the stuff I've highlighted in red, I'm only going to focus on these types of indexes today, because there's just not enough time to do all the others. There's probably not enough time to do these full justice, but we will go over them as best we're able. So again, I always like to set up everything up front. So if anyone wants to run away, you've got the opportunity, because you know what I'm going to be talking about. Now, when we start talking about indexes, we also need to talk about the fact that indexes have behaviors or properties. And some of the ones that are going to be really, really interesting for the row store indexes that we need to know about is the idea of a unique index. And this is an index that can only have one copy of whatever is defined as the key for that index. And the key is the column or columns that define the index. That can be unique. You can also have filtered indexes, indexes with a where clause. Those are a great utility, something to keep in your back pocket. You're not always going to apply them. In fact, you probably only rarely use them, but they are there. It is a tool. I've got a demo. We'll talk about it. Now, there's also the include operator, and this is for non-clustered indexes only, and it gives you the ability to add columns at the leaf level. We'll talk about what the leaf level is here in just a second. And then you can index on calculated columns as well. And so these are properties of indexes that are going to affect how you control and what you control in terms of getting your indexes in place. Now, the things you can do with an index, it's pretty simple. You can make them, you can get rid of them, you can disable them, which means not getting rid of it, but not enforcing it either, not having it available to the optimizer. And then you can enable it. And that's pretty much it. I'm not going to spend a lot of time on this, but I did want to make sure that we knew what you could do with them. So let's focus in on the row store index. Now, the concept of a row store is pretty, oh gosh, I forgot to re-edit the kangaroo thing. Anyway, my bad. The concept of the index is pretty simple. It has a series of pages, and this is in a B+ tree arrangement. It's not a balanced tree. If people are saying that, it's called a B+ tree. You can look it up online. I'm not going to get into all the scientific definitions of it. The idea is really easy. The first page shows you the beginning and end of the index. Below that, you have a series of pages that show you the other pages that are available to those pages. So ant to jackalope is one, kangaroo to rhinoceros is another, snake to zebra is a third. And so if we're looking for something like tiger, for example, it's going to go into the ant to zebra and say, are there any rows in this index potentially that match the value tiger? And it's going to go, well, ant to zebra, yes, there could be a tiger. All right, cool. Is it in the ant to jackalope? Well, no, it's tiger. Is it in the kangaroo to rhinoceros? No, it's tiger. Is it in the snake to zebra? It could be. Let's go look. And so then it goes down to the next page, which says, hey, I'm from snake to tiger. Well, heck, it knows now that it has a tiger in the index. It's going to go and retrieve that. Now, the neat thing is at the page level for a clustered index, that's where the data lives. And the reason most of the time, in most circumstances, for most people, is that enough weasel words? Should be. You should have a clustered index on every table. There are exceptions, but the exceptions should be exceptional. That clustered index defines your data storage as well as your data retrieval. And so, because it is the one, you only get one clustered index, only one, ever. One column store clustered index or one row store clustered index, you get one. That defines storage and retrieval. Therefore, it should be the most common path to the data. Now, for a lot of us, the most common path on any given table is the primary key. Cool, done, win. But sometimes the most common path is another column or columns. I lean heavily towards picking my clustered index based on the most common data retrieval mechanism. That could be, depending on the system, a foreign key instead of the primary key. It could be a date time column instead of the primary key. Could be anything, but we're going to want to define that up front because that's where the data lives. But with non-clustered indexes and the include operator, we then, down at that same low bottom of the screen page level, can store additional columns, making those indexes act like little artificial clustered indexes. They're not clustered indexes, but they act exactly the same way for the columns that you add. Cool. And this is basically the idea of the row store index. This is how it works. So data storage is actually a big driver for indexing. Now you can have a heap, that's pages only, no sort order, no particular order on the disk, no physical or logical ordering of the data whatsoever, just simply that double linked list at the bottom of that page. Here's where the data is, and if you need to find something, go and scan, do lots and lots of reads. That's the idea of a heap. The clustered index stores the data as we've just defined, and it stores that data down at that page level. And so you get both storage and retrieval with a clustered index. And then non-clustered indexes don't, by default, store any data. By default, it only stores the key values, in the case of before, an animal name, unless you use that include operator to add columns at that additional storage level. So that's that. And by the way, if it feels like I'm going kind of fast, I really am trying to cover all the information that we have. So let's get right to the ideas behind this session and talk about when and how we pick indexes. And we're going to start with the clustered index. Now, I've already said it, and it bears repeating. Most of your tables should have a clustered index by default. Period. End of story. Most of them. Are there exceptions? Yes. Exceptions could include, say, heap table where you're doing lots of data loads, massive data loads, and all you care about is the insert operation, and there's no need to worry about unique values. There's no need to worry about data order. You're never filtering any of this data. This could be a great place for a heap table. Again, it depends, right? It depends is always part of it, because we need to talk about the fact that you have to talk about data storage and data retrieval and inserts, updates, and deletes. It all matters. And this is why there's not a single formula that I can give you that you can follow. This is why there's not a, one solid path, one way to index databases. If there was one way to do it, we would all already know it. We would all already have defined it, and you would not be here talking to me today. So that's what the deal is. There's not a single path, sadly. So we need to talk about the ideas. And then once we've got the ideas down, we can talk about how best to apply those ideas. So first up, data storage is the clustered index. So you've got to think about that. Next, because the clustered index defines data storage, it also needs to be unique internally. Now, externally, it does not have to be unique. Internally, it must be, because you've got, say, 3 rows of data. If you make a non-unique value, let's say date, right? So it's February 10th, and you've got 3 rows that say February 10th, and you make that your clustered index. Well, we still need to be able to retrieve row 1 and row 3 independently. So inside of the clustered index, it will make what's called a uniqueifier. It's basically an identity column inside the clustered index, effectively, to all intents and purposes. That's exactly what it is. And it will make sure that it can hit one row uniquely. It can always find that one row. But you can have a non-unique column for a clustered index. That's fine. But know that you are adding some overhead because you have to maintain that uniqueifier. And if you're maintaining that uniqueifier, it is actually possible, it's pretty rare, but it does happen, to run out of uniqueifier values. And then you hit errors and all kinds of hell breaks loose, and it's no fun at all. But it's extremely rare. So don't freak out on your index selection and say we can only ever have unique for clustered indexes. Lean towards that, but don't limit yourself. Where possible, your clustered indexes should be narrow, meaning smaller data types are better. An int instead of a varchar 50, a varchar 50 instead of a varchar 75. Get the idea. Smaller is better where possible. That's not to say that if you've got, say, let's say 2 foreign key columns that make up a beautiful access path to your data, and they're unique, that's wider than the primary key. The primary key is not really used, but these 2 other values are, but we can't make them the clustered index because they're too wide. I would completely fight that and say, yes, indeed, we can make those two the clustered index because they are the most direct path to the data. Again, here, the whole idea is where possible, as narrow as you can. Don't feel like any of these things, these are all guides, not rules. You know, be nice to each other is not the same thing as the 10 commandments, don't kill people, right? All I'm asking you here is to be nice to one another. Where possible, you should minimize the involvement of inserts on a clustered index. This is because, hang on, I'm sorry. Sorry about that. My 22-year-old daughter still thinks that everything's an emergency. It's not. Anyway, the interesting thing about clustered indexes, because they define the storage and because they define the storage for non-clustered indexes, the more inserts you have, the more possibility of page splits you have, the more possibility of page splits, the wider the data gets split across. And you get into the whole thing of like, do I need to rebuild my indexes or not? Now, I lean heavily towards you don't need to rebuild indexes. This is not an index maintenance session, though, so I'm not going to get into that. If you want to, I know I saw his name come up. Jeff Moden is on here. Go look, track him down, and find out why you don't need to defrag your indexes. But I'm sure Jeff will agree with me. If you can minimize the fragmentation, you should. And that's one thing that you can do. So clustered indexes are best used for OLTP, meaning online transaction processing. Point lookup, meaning, give me one row. Clustered indexes are great for that. Key lookups, meaning the other index helped me, but I need to go and get data. Clustered index. And they are good for scans because it's storing the data. It means you can scan one place and you don't have to go anywhere else to get the data. That's roughly your clustered index application. Non-clustered indexes. Let's go through these. First up, make as few as you can. Now, I am not one of these one true index people, and they're out there, people who are like, you can have one index, you get one, preferably a clustered index, but you get one index because any additional index is overhead, and overhead can't happen, therefore you get one index, we're done. Problem is, queries don't work like that. Businesses don't work like that. Reality doesn't work like that. There is more than one way to look at data. This is why object-oriented database designs inside of relational data structures fail so horribly, because they only have a single path through to the data. And as soon as someone says, cool, can I also slice it by date or look up the first name, and suddenly that whole object schema just falls apart. But we want as few of these as possible. So resist that urge. You get it. I get it as a DBA. You get it as a DBA. Developers absolutely get it. Things are slow. Add an index. It's acting weird. Add an index. It's not behaving exactly the way we want to. Add an index. If we can just throw indexes on it. No, as few as possible. Now, that's not to say none, and that's not to say that if you think you need one, add one, do it. But keep them to a minimum. On non-clustered indexes, again, keep the keys as narrow as you can. Can you always keep it narrow? Can you always have just an int? No, of course not. But you keep it as narrow as you can. Don't like, well, we'll add some extra columns just in case. No, because it does add overhead. It does add width to the index. It slows down the use of the index because it has more pages that it has to walk through. We can deal with statistical skew by using filtered indexes. Another great place to use filtered indexes is if we have a sparse column, meaning a column with only a few data points in it, and then otherwise it's null. We can filter out the nulls, and then our index becomes more useful. Or if the majority of our data is all on one date, but then we've got like a million rows scattered across, we could filter out the one date or filter in one date. There's a whole bunch of stuff you can do, but keep that in the back of your mind, mainly focused around statistical skew. Now, Non-clustered indexes are extremely helpful for OLTP queries, certainly in point lookups, right? Go and find me everyone with a first name of Grant. Or for short scans, go and find me first name for everyone with Jean and track those down. But it's not so great for big scans, because generally if it's got a big scan, it's also going to have to go to the clustered index and look up data there. For analytical queries, the non-clustered indexes are good for point lookups, but analytical queries analytical queries are not supported well by row store indexes. They're better supported by column store indexes. All right, normally I would go to the demo here, but because we have so much to get through, I want to go ahead and keep talking about the column store indexes, and then we'll go do demos. Column store indexes. All right, so the idea of a column store is pretty straightforward and simple. This is what a row looks like. So row store, ID 1, Grant, he's a doof, and here's his date. ID 2, Jeff, he's not a doof, here's his date. Gabby, and you see the ideas. This is the row store. In this case, the unique index is obviously the ID. Somebody messed up the database design because there's not another natural key on it. So this is really a poor table, but you get the general idea. If we pivot it to column store storage, it looks like this. What we've done is we've eliminated the whole idea of rows of data, and now we're focused on columns. So the ID, which is unique, we still have 7 IDs, but the names, we're only going to have Grant, Jeff, Gabby, Ahmed, and Suzanne, because we're not storing duplicate values anymore. The descriptions are doof, not a doof, and smart. The dates are limited to the dates that we have ranges for. So we are no longer looking at all the data. We have pivoted the data into column storage. We have eliminated duplicate values. And on top of that, they are compressed. All of this is data compressed when it's stored. And so the way it gets stored is each column is broken down into a column segment, and then there are row groups across those columns. And finally, in addition to all that, there's this thing called the delta store. And the delta store is data changes coming in over time. And the delta store is nothing but another B tree index, good old fashioned B plus index inside of the column store index. It's stored there until it hits 100,000 rows. Once it hits 100,000 rows, it will then automatically get moved back up into the compressed, happily deduped column indexes. So column index use. Few things about it. It came out in 2012? Yeah. And then the clustered column store was introduced in 2014. If you're on 2012, don't worry about column store indexes. One, it's 2012. You're on a 9-year-old system. It's time to upgrade. But if you're on 2012, don't worry about column store. They work, but they are read-only and non-clustered only. So it becomes very problematic because they're read-only. But there are other limitations. Prior to 2016 SP1, it's enterprise only. So if you're on 2014 standard, you won't get column store indexes. The clustered column store was introduced in 2014, and the clustered column store is amazing. Memory optimized, it's 2016 plus. B tree indexes on top of your column store indexes are 2016 plus. Filtered column store, and you can do filtered non-clustered column store, is 2016 plus, and everything works inside of Azure. So just move everything to Azure. Kidding, totally kidding. Totally, that was a joke. Don't do that. Now, there are limitations for column store. You can't do any of the max columns, varchar max, the rest. You can't do text. You can't do any of the CLRs. That includes spatial or hierarchy. XML, not allowed. And then GUID is limited on 2012, but it's available in all the others. And then obviously SQL variant, which is, as far as I'm concerned, a massive feature, not a bug. If we could eliminate that data type, I would be in favor of it. If you're going to use column store indexes, you can't use that data type. So that's a win. I don't care if anyone disagrees. All right. So non-clustered column stores. One, max of 1024 columns. No sparse columns. You cannot use alter index. You have to use drop and recreate. There is no include because it's just not a concept. And you can't do ascending or descending because, again, not a concept. So limitations on the clustered column store. Persisted computed columns are 2017 and above only. You do get page or row compression. You can use them with replication. Oh, no, I'm sorry. You can't use them with page or row compression. You can't use them with replication, and you can't use them with file stream. Snapshot isolation supports 2016 and only. Above, column store on table creation is 2016 and above. Availability groups 2012 and above. Partitioning 2012 and above. All right. All right. I got rid of all of the junk. Now let's talk about why we want to use column store. The beautiful thing is we got to talk about the types of queries. If you're talking about a point lookup, I'm returning one row or a small set of rows, 10 out of a million, 100 out of a million. Column stores are worse than row stores. So there's nothing magic in column stores that makes it so, hey, just put a column store index on, every query runs faster. It's not at all how it works. It's very dependent on the queries. And I lean extremely heavily towards only analytical style queries, meaning group by XYZ, average, sum, all that fun stuff. Analytics on your data. That's where column store shines. Or in massive scans. If you're scanning everything, column store actually scans faster than than the row stores. One, I'd avoid massive scans if I were you. It's kind of a bad problem. It means you're touching everything, and so it leads towards poor performance. But that's how things go. So why are column stores faster? Why for analytical queries? First up is data compression. As we showed, when it pivots the data and it does elimination, you're storing less stuff. And the fact that it's then compressing that data and storing it on a smaller number of pages, yes, you have to sacrifice CPU to get it in and out, but you're going to get a performance increase. You also get column elimination. If you're not referencing a column, because it's column divided, it doesn't need to look at that column. It just ignores that. And that's all those pages, all those row sections, all of that stuff is just taken away from the processing, and therefore things get faster. You also get row group elimination when you've got a where clause that it can look at and say, well, within this row group, I know what the start and stop points on the data are. I don't need to look at this one. I don't need to look at this one. I can just find the ones I need to look at and pull back the data I need to look at. You also get batch mode execution. Now that's available in 2019 a little bit in a few places for row store. It's not real common. I'm not going to demo it today. For row store, I will demo it for column store. But batch mode execution is amazing. I'm not going to explain it until we get to it. You also get aggregate pushdown and string predicate pushdown. String predicate pushdown is meh. It occasionally works, and when it works, it's great, but it doesn't work real often. Aggregate pushdown is easy to understand because the data is stored in batches in the column. If you say sum this column, well, heck, SQL Server can very quickly add those columns up without needing to read the columns out first. It just sums them as it reads them. Ooh, cool. That makes for performance enhancements. String predicate pushdown is the same kind of idea. The filtering can be pushed down at data retrieval and ensure that fewer rows are read inside the data to retrieve it back out, or pages. Sorry, I said rows, pages. But it doesn't always work. So anyway, batch mode execution. Oh, I do have to explain it. I was going to explain it in the demo. Matter of fact, I'm going to explain it in the demo. It's easier to understand when you can see it. Where to use column stores? Well, first, determine the access path. Is our access path primarily analytical? Cool. Clustered column store for the win. Is our data access path primarily OLTP? We probably want to stick with row store and then look at non-clustered column store. So we determine data storage first. Then, how does our data get loaded? Do we have a trickle load going in a few rows at a time, all day long? Column store is probably not going to be your buddy at that point because it's going to do two load processes, one to the Delta store where it accumulates, and then a second to the compressed, beautiful column store stuff. Column store works better for batch load processes, just does. Because if you can load it all up at once, it puts it all in at once. Also best to break it up in 100,000 row batches, but cool. Third, your queries, analytical or non-analytical. Fourth, the Microsoft says 1 million rows are better. My testing says 100,000 rows are better. Either way, you pick your call, it's larger data sets. If you're looking at 10,000 rows, column store is not going to be your buddy. It's just not. It's the data set's too small for all of the benefits to be achieved. I would look only at 100,000 rows and up. And then from there, you can mix and match, because if we're looking at 2016 or above, create a clustered column store, because our primary data access path is analytical. Cool. But we occasionally have point lookups. Awesome. We will then put non-clustered row store indexes onto our clustered column store to retrieve those occasional point lookups. Win. Or conversely, we are primarily an OLTP system with lots and lots of point lookups, but we have the occasional analytical query. So we're going to put a non-clustered column store onto our clustered row store. Win. Again, both choices are valid depending on the query types that we have to support and our data. So you can see why, after all the stuff we've gone through in the last half hour, there is no way for me to give you a formula that's going to walk you to a particular index for a particular scenario. You have to work through all the details. When do you use them? Fact tables, absolutely great choice. Large dimension tables, also very good choice. Data warehousing in general, because that's usually where we're doing large scans and lots of analytical style queries. If you're doing analytical queries, or if you're doing aggregation queries, or if you're doing large scans, these all are well supported by the column store index, whether clustered or non-clustered. It's just a call on what you think you need to do. All right, now it's demo time. By the way, I don't see the chat on here, so if there's any questions, I'm not sure where you guys can put them. But we've got 20 minutes. Let's go play with code.
I will read the questions.
Okay, cool. Are there any outstanding right now?
No.
Okay, cool. And by the way, if anyone wants to ask a question, feel free. All right, so I've got a query. I'm going to go ahead and turn on execution plans. So a few things that we're not going to, oh, nuts. Nope. I forgot one thing. We got to spend another 5 minutes real quick. Whew, statistics. DVCC show statistics. There it is. 3 bits of data. Your header, the density graph, and the histogram. Why is this important? Because this is how the optimizer makes choices. The optimizer makes choices on which index to use based on this information. This information gives it row counts. So if we're looking, say, at the value Ballard, oops, get back here. If we're looking at the value Ballard, we can say that there are 69 rows that match the value Ballard. But let's say we were looking at the value Ballardia, right? Spelled almost exactly the same way, and it falls between Ballard and Beaverton. Cool. How many rows are in that? Well, we don't know. What we can tell you is the average range rows for stuff between Ballard and Beaverton is 1.5. So it's probably going to be 1.5 rows-ish. That's all we know. And so that's how we start making those determinations. The whole idea is the selectivity drives these choices, and that's the number of values possible over the total number of values. The histogram is a big driver, as we just walked through. Hey, look at that. New camera came on. Then you start looking at the density, which is 1 over the distinct values. And then we start talking about compound keys. Now, prior to 2014, that was easy to understand. It was selectivity times selectivity. 2014 and up, we have what's called an exponential backoff, meaning it does selectivity for first column, 1/2 of the selectivity times 1/2 of the selectivity for the second column, times 1/4 of the selectivity for the third, times 1/8 of the selectivity for the fourth, et cetera, et cetera, et cetera. Now, joins, you get really fun stuff. This is where things get interesting. Now, simple joins, straightforward joins, it's a linear matching. 2014 starts doing min-max on the histogram, which is really complicated. Compound joins is selectivity times selectivity until we hit 2014, in which case it goes through the smaller selectivity value. When we start getting the estimates versus the cardinality, we have to compare values. When we start talking about estimates versus cardinality and we start seeing skew or bad estimates, this is why we're comparing variables, at variable to at variable. SQL Server doesn't know what it is, it makes guesses. Using not equals or not. SQL is, again, going to have to scan stuff to make determinations. It can't do row counts based on not. Predicates, comparing columns within a table. As soon as we start comparing 2 columns, it can't make row counts. It has to go and guess. Functions without a constant value, meaning min, max, stuff like that. It has to do calculations, and therefore it can't get row counts. Joins using arithmetic or string operators, trim, ltrim, rtrim, they keep it from getting row counts. If you don't have statistics, you don't get row counts. And then if you've got skewed distribution, it's not so much that you don't get row counts, but that you can't trust your row counts. If the data is not in statistics in 2012 or less, you get 1 row. 2014 or greater, it's all density of the statistic times the number of rows. Awesome, I've covered the stuff I needed to cover. Yes, all right, now let's go play. Sorry about that. So if we look at a query, and I've got this one, and we're going to run it and capture the execution plan. Oh, one other thing. Execution plans are not performance. So you do need to make sure that you're also capturing performance anytime you're looking at indexes and picking and choosing indexes, because it is all about performance, and therefore we need to look at query performance. There we go. Come on. Start that session and watch live data. Cool. All right, so this query performed. Let's go ahead and run it one more time without the execution plan, so we can see how fast it performed and the number of reads, because you don't want to rely on any one value. Just knowing reads doesn't tell you performance. Equally, just knowing duration doesn't tell you performance. You need to look at both, because both affect the other. It could be that all the processing occurs in the CPU and very little is occurring on the reads. Or there's lots of reads, but I'm on a system with no contention, and therefore performance looks great. And then as soon as you get on a system with contention, performance stinks. So you need to be able to look at both to understand what's going on. But if we look at the execution plan, it's pretty straightforward. It's doing a select operation. It's doing 2 nested loop joins to pull data together, 1 index seek, 1 index scan. And it's an index scan across 1,000 rows. Now, this is a demo database at VentureWorks. In the real world, would I care about 1,000 row scan? Probably not, depending again. But for our demo purposes, let's say it's a 1 million row scan. Let's say it's a 10 million row scan. Now, do we care about it? Oh, yeah. Yeah, now we care about it all of a sudden. So what's going on with this? Well, this is the primary key of product inventory. It's able to retrieve some stuff based on the location name. That's great. And it's doing a clustered index seek for the product ID from the product table. So we look at the query, we can see it's going to product inventory, and the production location. It's able to use indexes for 2 of the 3, but not for product inventory. So what do? Because it's limited number of rows. If we look at this, it thinks it's going to get 1 row. It's estimated 1 row, it's estimated 1 row. It's actually 1 row. So it's a very efficient query, except for this silly scan. So let's fix it. Well, how? Well, what's it scanning on? What's it referencing? Well, it's product inventory. Let's go back to the query, because it's always driven by the query. Well, the only things it's referencing for that are location ID, product ID, and shelf. And shelf is not filtered, it's just returned. So as a thing that's returned and not filtered, it's an opportunity for the include operation. So we can say, you know what? Well, product ID, it's joining on product ID. If we join on product ID, because the product ID is only retrieving 1 row, surely if we create this index and then we rerun the query, we should see a big difference, right? Well, the answer is no. We get it, we're not seeing the clustered index scan anymore, which is yay, but we're still seeing an index scan. We're still retrieving 1,000 rows. It's not a win. There is just not enough time to do this. I'm going to have to do like 5 of these, 1 for each index type. Anyway.
By the way, you can take your time, Grant, and I have unmute give everyone access to unmute themselves in case if they have any question to ask you.
Okay. So let's try another one. Here's the deal. We know that we're filtering on product ID, but we're also filtering on location ID. So let's try adding that stuff in. We'll go product ID and location ID. And if it sounds like I'm just experimenting, I am. I know what the answer is because I've already done this experiment once, but we'll run this and we get the execution plan back. And again, it's just doing the index scan. The new index didn't even get used this time. Now, what's going on? Well, here's the deal. We're not helping ourselves because we didn't stop and consider what indexes were already on the table. So we go take a look at this table. And we see the indexes, and they've got a pretty nice naming standard. I'm not crazy about it, but we've got one index, product ID, location ID. That's the primary key for the product inventory table. And by the way, 2 foreign keys on that table, which is a great choice for a lot of indexes, because that's probably the common access path. But in our case, it's not helping us. Why? Well, product ID is the first column for that index. Now, if we look at the 2 indexes we tried, both of them also had product ID on the first column. Now, if you remember our statistics, that means the histogram is on product ID for those 2 columns and for the clustered index. Now, why would it pick that non-clustered index for the scan after we created it instead of the clustered index? Because it's smaller. And the optimizer's smart. It says, hey, you know what? Both of these indexes are going to retrieve the data that I need. I'm going to have to scan either one of them. But this one's smaller because it's a non-clustered index. It's only got the 1 column, product ID, and the shelf. So I don't need to look up anything else because it's got everything I need because the location ID is the primary key, and the primary key is included with a non-clustered index. So we've got all the data we need to make this a covering index, and so we can do a scan there. But it's a scan. It's not helping us. What if we tried this? Let's put an index on the location ID. Now, what we're doing is we're taking an index that already exists, product ID, location ID, and we're actually reversing it because the product ID is still going to be included as part of the primary key. So we've got that available to us, and we've got the location ID now as a leading edge. That means we get row counts, and row counts based on location ID. If we also include the shelf, and now we run our query, the execution plan changes. 1, 2, 3, nice clean index seeks, one clustered index seeks, and the nested loops join. Cool, yay, that's a win, right? We won. No, not yet. Let's take a look at performance. First off, turn off the execution plan, because execution plans and performance measurement don't go hand in hand. All right, now let's take a look at the query. 22 reads 305 microseconds versus 29 reads 4,000 microseconds, 4 milliseconds. So under a millisecond versus way under a millisecond, a third of a millisecond versus 4 milliseconds. Now can we say that we have a performance increase? Yes, absolutely. We can say that without prevarication. It is a performance enhancement. So that's how we do indexing. It's a bit of a guesswork. It's an educated guesswork because you need to understand how indexes work, what indexes are, and then make those choices accordingly. Now, I've got examples for key lookups. I've got examples for subqueries, and I've got examples for how to clean this up. Like I said, I put way too much data into this presentation. There's just so much to know. So let's take a look at this. Let's see, can we do this? Let's take a look at this query. Oh, I need the execution plan. Well, let's take a look at the performance first. Performance is an untold stupid number of reads and an untold stupid duration. It's big, it's slow. Let's take a look at the execution plan. And we see that it went parallel because the cost was high enough. And it is using a column store index. So it's able to use this column store index, and that's great. But the performance is still kind of crappy. Well, let's do this. What if we oh, that's what I did wrong. Hang on 1 second. Sorry, I'm an idiot. I forgot what I was supposed to do. Right. There we go. No, it's still doing a clustered index scan. Huh. Where did I mess that up? Well, anyway, let's talk about batch mode processing. Let's get the execution plan. There we go. Now, a couple of things about this. Now, it's already using the column store index scan. You're only ever going to see scans on column store. Don't worry about that. That's all you'll ever see. It's okay. It's just how Microsoft chose to do it. There's not a seek and a scan. There's just scans. The key, though, is are we getting data retrieval, and are we seeing this little booger right here? Come on. Batch mode processing. Now, batch mode processing is really simple. If we look at another execution plan, the way execution plans normally behave is the select statement says, hey, give me data from the parallel gather streams. And then that says, okay, cool, I don't have any data. Let me get a row from the adaptive join. Well, the adaptive join is a bad choice. Hang on, let's get a different execution plan up just so we can talk about this like intelligent human beings. There we go, this will work. Nope, that didn't work. That's a bad choice. This will work. Right, so it's pulling one row from the nested loop join. The nested loop join says, hey, give me one row from the other nested loop join. That one says, I don't have any data. So it goes to the index seek and says, do you have any data? Yes, it returns a row if it finds a row. That goes back to the nested loops. The nested loop says, hey, do you have any data down here in the clustered index seek? Yes, I do. And it retrieves it and pulls it back up here. That then passes the matching rows back over to this nested loop, which goes to get the clustered index seek again, returns that and pulls that on across. And it does this for each row, one row at a time. Now, the last time I gave this presentation, like I said, I've only given this presentation one more time. Someone says, well, why did they just do one row at a time? Like, I don't know. That's how they did it. that's how they wrote it originally. It does one row at a time. That's how the query processing inside your system works. Row mode processing, and we can see that these are row mode processing because it shows it right over here. Execution mode, row. Row mode processing is one row at a time. Now, let's take a look at our column store. If we look at our column store index, I've got to clean that up. What that's doing is batches. And so it did 36,000 batches. And the way the batches work is it's anywhere from 60 to 900 rows. I usually tell people, think 1,000. It just makes it easier to do the math. But it's somewhere between 60 and 900. And if you look at the math there, it does break down the actual number of rows versus the number of batches. It makes sense. It says, hey, I need data. Give me 1,000 rows between 60 and 900. It then moves that 60 or 900 rows across. And then as each operator does that same thing, it's always the same. It's always give me 60 to 900, give me 60 to 900, give me 1,000 rows, give me 1,000 rows, give me 1,000 rows. If you think that moving 3 million rows, one row at a time, is slower than moving 3 million rows in 36,000 batches, you would be right. One row at a time is radically slower. So the batch mode processing is an internal methodology within SQL Server that makes the column store way fast. And you can look at each of the operators to see whether or not it's operating in a batch mode process. And then finally, when it gets to row mode. So the parallelism gather stream, because this query went parallel, the gather streams operation is row mode. So that one is calling one row at a time for the, 25,000 rows that it needs. So that stuff has all been aggregated down, filtered down, and off we go. Yay, we win. The other mention I wanted to say about column store indexes is the push down predicate, or is the push down aggregate. And so what we get is it was able to aggregate a lot of the data as it read it. And so therefore, instead of this aggregate having to aggregate everything, it aggregated a subset of the data. It pulled out 100,000, or is that 10 million rows? It pulled out 10 million rows prior to aggregation. And then so it had to aggregate fewer data down to the, what do we end up with? 25,200 rows. So it eliminated a bunch of stuff by pre-aggregating that data, which is fantastic. It's a great resource. It's a big win. And that's why analytical style queries are just so much better. Now let's see. No, I already did that. I didn't clean up the data tables that I should have cleaned up. All right, looking at the time, we are officially out of time. I've got some more time. If you guys are okay, I can hang around. I know we had a 5-minute delay with the sound. So I mean, we can hang around for a couple more minutes. And I've got to figure out where else to trim things from this session. Let me just go back and get to the summary slides. So clustered indexes, OLTP situation, row store clustered indexes, thus the preference. It's based on data storage first, and then speeding things up second. Non-clustered index is all about speeding things up. And as a matter of fact, it sacrifices data storage in order to speed things up. You are looking at point lookups and short scans. Column store is all about those aggregate queries, those analytical queries, those large scans, big data sets. So index selection, first, determine your data storage, because data storage drives everything. Second, for row store indexes, focus on unique data. And third, for additional indexes, regardless of how you do it, as needed. And then just remember, every index you add does add overhead, but that, most systems read way more than they write, like by leaps and bounds. Because you got to remember, every update query reads, every delete query reads. Insert queries are the ones that only insert, but everything else reads as well as writes. So you got to think about the fact that you're doing a lot of reads on most of your systems. So yes, there's overhead to indexes, and it's specifically around updates, inserts, but you have to make that sacrifice. All right, cool. I've got to trim some data out of this presentation. Any questions?
I got a question, Grant. Can you hear me?
Yep.
First of all, I have a statement. It's really great to speak with you directly, not through chat.
Who is this? I can't.
Dwayne, right?
Hey, how you doing?
Been a long time.
Yeah.
And I'm hoping PASS gets resurrected so we can see each other again.
Yeah, we'll see what happens.
Yeah.
That's all I'm gonna say. But yeah, I do hope we get back to in-person events.
Yes.
Rather than later.
Quick question. Could you compare or maybe contrast the conceptual difference between execution mode, row or batch, versus the more conventional concept of rebar or set based?
Well, funny enough, batch mode is more like set based operations, and frankly, row mode is rebar effectively. It's like rebar is built into SQL Server.
Right. So batch mode, before batch mode,
everything was row mode.
Everything was row mode, but you could still get into this situation of doing rebar for like cursor operation, right?
Yeah.
So is the concept that the internal engine previously was always doing rebar internally, whereas how you do your query, worst case scenario, a cursor, right?
Right.
You were actually going into the execution engine and then out one row at a time.
Right.
Is that the concept?
Yes, very much so. You've nailed it. I'm just trying to find a good query to explain one bit. Give me 1 second, and then I will answer the question further. Perfect. Perfect? No, not perfect. Bad, in fact. Bad choice. Let's see. I'll bet this one does it. Yes, perfect. All right, so this is row mode processing. We can validate that if we want to. The execution mode is row. Cool, when? The select pulls from the compute scalar, which pulls from the nested loop, which pulls from the sort, which pulls from the index scan. Index scan returns a row. It's a sort operation. Sort operation has to order the data. This is what we call a blocking operator. Unlike the other operators, which are effectively pass through. I've got a row, I feed a row. I've got a row, I feed a row. I've got a row, I feed a row. Blocking operators are like, cool, I've got a row, you get nothing, because I've got to get all the data first. And so it sits there saying, do you have a row? 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 Until it gets everything. And then it does the sort operation. And once it's done the sort operation, then it passes over its first row. So that's a blocking operator. By the way, the hash match aggregate is also a blocking operator, and the table spool is also a blocking operator. And there's not a perfect list of blocking operators, but if logically you look at what each operator does, you can guess which ones are blocking. And that also then determines parts of how row mode processing works. Hope that helps.
Yes, thank you. And by the way, chat wasn't available in the window for me. That's why you weren't getting any questions.
Yeah, well, I was trying to keep an eye out. I couldn't see it anywhere. So
I hummed a Rocket Gene through LinkedIn and said, hey, the chat window's not available. You might want to unmute everybody near the end. And that's why you're unmuted. So
I know that voice.
Ho, freaking ho, right?
Awesome. Good to hear you,
So
Jeff.
Grant, where is the what did you say, 2 or 3 hour session? Did you record that?
It was recorded, but it was a private session I did for consulting. And it was 2.5 hours, and I still didn't get to the statistics.
Yeah, you do need to break this up into one session per index
there's
type.
just so much data. And I thought by eliminating all the extraneous indexes, I really thought I'd narrowed it down, but there's just so much to know. Any other questions?
To be honest with you, that was a great session. I learned so much, Grant, and it will be an honor to have you another time, sometimes next year.
Next year? What?
or this
No,
year,
teasing.
even if you are available. It's right. Yeah. Are there any more questions?
No, but nice job, Grant.
Oh,
Appreciate
thanks,
it.
Jeff.
Thank you, buddy.
From you, that means a lot.
Thank you, sir.
All right, I'll
If
stop sharing.
there are any more questions, we're gonna end.
Great. Thank you very much. Very helpful.
Oh no, thank you all.
So much, Grant, and thank you, everyone. Yeah, thank you.
Great. Have a good day.
See you guys.
Bye.